All right, this is something we're going to need at times throughout the rest of the semester. It's been a while since we've talked about Pythagorean theorem. Probably might even have been Algebra 1, because I don't know if we've talked about the Pythagorean theorem much at all this year. We've talked about right triangles, but we haven't necessarily talked about the Pythagorean theorem and how it relates to right triangles. But first of all, in a right triangle, we know that we have a 90-degree angle, right? We have three sides. The two sides that touch the 90-degree angle are called the legs. And those two sides are interchangeable. I could call this one A and this one B. Doesn't really matter which one's which, but they're both legs. Okay, C is what we call the hypotenuse. There's a couple of different ways that we can identify the hypotenuse. One way is that it's always opposite the 90. There's only one side in that triangle that does not touch the 90. That's my hypotenuse. Okay? It's also the longest side, but that sometimes may be hard to determine. If I don't know what the length of A, B, and C are, then just by looking at that, I may not be able to determine which side's the longest, but I can always say it's the side opposite the 90. And when we say opposite the 90, it's the side across or the side that does not touch the 90. Okay? And there's only one side that doesn't touch it. That's my hypotenuse. Okay, so this is what we call the Pythagorean theorem. The formula for the Pythagorean theorem is a squared plus b squared equals c squared. A and b can be interchangeable, okay? Because A and B are always the legs. And then C is obviously the hypotenuse. So where I put the hypotenuse is the most important spot. These two can go and trade places and flip-flop one another. We're going to do a couple of problems where we're solving. Basically what we're going to have is we're going to have a right triangle. We're going to be given two out of the three sides of that triangle, and we're going to try to find the missing side. What would the third side have to be? So right away, I know these two sides, okay? These two sides on number one, we're not going to do all six of these, but this is A and this is B. And I could flip-flop them. I could say this is A and this is B, so it doesn't matter which one's which, just so you know that those are okay. And then this is obviously my hypotenuse. The one thing we know right now is that this side must be longer than these two, because it's the longest of the three sides. So it's got to be bigger than 8 and 7. I won't rewrite this every time, but I'm going to write it down since this is the first one we're doing. We're going to plug in numbers for A and B, or whatever values that we have. So 8 squared plus 7 squared equals c squared. Okay, and then we're going to solve it. So 8 squared would be 64. 7 squared would be 49. Which is 113. And then to finish it out, we take the square root. Okay, the directions say here, let's round to the nearest tenth. Okay, if you have your calculator, let's get it out and just try putting this into our calculator and make sure you know how to punch in square roots and all that. If we round to the nearest tenth, that's one decimal place. So we look one place to the right of this, and if it's 5 or more, we round up. If it's less than 5, we keep it the same. So this should round up to be about 10.6. So we're saying this length here, this side, would be about 10.6, which is bigger than both 8 and 7, so it would make sense. Okay, if I look at number 3, the one side that matters here is this one is C. That's got to be our C value. The other two, it really doesn't matter. I'm going to call this one A, and I'm going to call this one B. And we're going to take those numbers, plug it in. Okay, this is a little bit different because this time we're given C. We know this must be the biggest side on the triangle. So we got 36, 169. And then we're going to subtract 36 from both sides. And we're going to take the square root. What do we get if we round that to the nearest tenth? 11.5. Okay, and we always want to make sure our answer makes sense. 13 is the biggest side, 11.5 is definitely less than that. So as long as it's less than that, then that would make sense with what we've got. Okay, on number 5, which one matters? Which one do we got to make sure that we identify as the hypotenuse? 20. Okay, so this is our C. These other two could be either way. So then we get 144 plus x squared equals 400. Subtract 144 from both sides. And we always finish by taking the square root. Okay, so we won't always get a decimal. Here we get a nice whole number, 16, okay? We will get decimals sometimes, but if it says round to the nearest tenth and I don't have a decimal, you don't necessarily have to put a decimal there.
I was putting B instead of X. Is that considered?
Yeah, nope, that's okay. Because X and B are the same,
Okay.
so I would be okay with that. Okay, any questions? You guys kind of remember the Pythagorean theorem, probably from Algebra 1, doing that a little bit before. We're going to see that the rest of the year, really, even going into next semester, we're going to see the Pythagorean theorem quite a bit. So it's something that we definitely want to make sure we got in our tool bag of things that we need. Okay. We have two different things that we're going to talk about. What I told you at the beginning of chapter 6, right before the break, was that we, the problems that we're going to be given here are not necessarily real difficult solving problems, but we got to be able to understand the differences between each one of these pictures and what's going on. How do they all relate to one another, essentially? Today we're going to talk about two big parts of a triangle. So we have a triangle here, and that's what we're going to see over and over again in all of these problems, is we have a triangle, but I have different pieces in relationship to the triangle. So in this case here, before we talk about the circumcenter, I'm going to come down here and I'm going to talk about what we call a circumscribed triangle. This triangle is circumscribed because it has a circle that goes all the way around it and touches at all 3 points. Okay? A, B, and C. All touch the circle. And the circle goes around the outside. You can kind of think of the word circumference. You've heard the word circumference before. Circumference means around the circle, right? And here we're talking about circumscribed. So when I go around the outside of the triangle with the circle is what we talk about when we talk about a circumscribed triangle. Now, there's a lot of different ways that this could be seen here. First of all, if we have a circle that goes around an acute triangle, P is the center of that circle, and the center of the circle is on the inside of the triangle. Okay, so P is the center of the circle and P is inside the triangle. Here, P is the center of the circle, but P is on the triangle, and it's a right triangle. So when I have a right triangle, then P will always be on the triangle. And finally, if I have an obtuse triangle, then P will be outside of that triangle. Okay, so in all three cases, we have a circle that goes around the outside of the triangle. It touches the triangle in all 3 points, right? But where those points meet is going to either be inside, outside, or on the triangle, depending on what type of triangle we have. Okay, so that's what we talk about when we talk about circumscribed triangle. Now, if I was going to do that up here, and this isn't going to look great, but at least you kind of get an idea, because I'm going to kind of freehand this. If I were to circumscribe around the outside of this triangle, okay? We have a circle that goes around the outside. P is the center of the circle. But P is what we call the circumcenter of the triangle. Okay, so P is 2 different things here. It's the center of the circle, but it's also what we call the circumcenter of the triangle. Well, what does it mean to be a circumcenter? Well, the circumcenter has a couple of different things. The 3 perpendicular bisectors meet at the circumcenter. So notice what's going on here is, here's the center, P, right? If I were to draw these 3 segments in here, these 3 segments are the perpendicular bisectors of that sides of this triangle. And we know it's perpendicular bisector because it's 90 and these 2 sides are congruent, or these 2 pieces are congruent. So D is the midpoint of this side. Here, E is the midpoint and it's perpendicular. Same thing here. We know these 3 sides are definitely not the same length, okay, but they are all the perpendicular bisectors of those sides. The sides that are going to be congruent here are going to be these 3. Okay, so what we're going to say here is BP is equal to AP is equal to CP. All 3 of these pieces will be the same. They're the same length. Okay, so we're connecting the circumcenter to the vertice of the triangle. P goes to C, P goes to B, P goes to A. Okay, and that's a really important piece of information. Because if I look at this picture down here, it's the same picture, okay? But based on everything that we just talked about, I can say PA is equal to BP is equal to CP. These 3 pieces connecting the circumcenter to the vertice of the triangle are all going to be the same. Now, I called it CP, they call it PC. Is there any difference between those 2? No, they're the same thing, right? PC, and you call it PC, I call it CP. We're talking about the same side. It's the same segment, okay? But when we don't have a symbol above it, we are talking about distance. So CP here is 12. They tell me that PC is 12. Well, what do you think that means about PB and PA?
No.
They're all 12, you bet. So PA is 12 and PB is 12. That's all there is to it, okay? Not a whole lot of math, but that's why it's important to understand the relationships that are going on, because then all I gotta do is be able to recognize what's going on and identify that those three pieces are all congruent, okay? This one here is very, very similar. Once again, it's the same picture. So once again, I can say PA is equal to BP is equal to CP. And it doesn't matter how you write it, PC, CP, whatever, okay? Now, they give me two pieces, AP and BP. And what we just said is that those two pieces are equal. We're not even talking about CP right at this moment. But what I'm going to do here is I'm going to write that AP equals BP. And what they give us is they give us an expression. They don't actually tell me the length of each one of those, or even one of them like they did here. They just tell me an expression. So we know that AP is really x plus 4. So we're going to plug x plus 4 into AP. We know that BP is really 2x minus 7. So we're going to set those two pieces equal because we know they're the same length. And then we're going to solve for x, okay? I mean, how many times have we solved an equation like this for x? Many, many times, right? We should hopefully be able to do that. We subtract x, we add 7, and we get x equals 11. Okay? And I'm telling you right now, this is probably one of the biggest mistakes, especially on big ideas that people make, is they say x equals 11, they type 11 into big ideas, and they're like, okay, I'm done. But the question's not asking me what is x. If it says what's x, I am done, right? But it wants to know what is PC. So here's what I'm going to tell you. We know PA and PB. PA is x plus 4. We know PB is 2x minus 7. It doesn't matter which one of these I plug it in for. I can plug it into either one, but here's what I'm going to tell you. I think it's important to plug it into both. If I get the same answer for both of these, then I know that I've done something right, okay? And it doesn't take that much time. All we're going to do here is take 11 and we're going to plug it in. And this would be 11 plus 4, which is 15. If I do it here, it would be 2 times 11 minus 7, which would be 22 minus 7, which is 15. If these two are the same, that's good news, right? Because we said those two should be equal. They are indeed equal. So now if I wanted to find PC, there's nothing to plug it into. But what would I say about the length of PC? How long would PC be? 15. Because all three of those are the same. But the fact that I know these two are the same, that's good news. And then I know PC must be the same as those two. If these two are not the same at this point, I've done something wrong, okay? That's why I think it's important to do both. It doesn't take that much more time, especially on a quiz or a test, just to verify that those two are indeed equal to one another. Okay, so that's what we call a circumcenter. When we looked at this one, it was perpendicular, but it also split it in half, okay? That's not happening here. So that's the big. The second thing that we're going to talk about today is what we call the end center of a triangle, okay? The end center, in this case, this circle is inscribed. Inscribed means we're going to have a circle on the inside of the triangle. Not only is it on the inside of the triangle, but it touches the triangle at all three edges of the triangle. We call that a tangent. It's a tangent point because it touches it at one point. We'll talk more about tangent later on in the year. But right now, we're seeing that that circle's on the inside. And so when I think inside, inscribed inside, both talking about in the circle or in the triangle. In this case, we're looking for point P. Point P is what we call the end center of this triangle. If I connect P to the edges, okay, now what we said before is that these three pieces would all be congruent. Well, that's not the case here. Okay, these three pieces are not going to be congruent on this one. Okay, so we got something else that we're going to look at. One thing that will be true is when I take P and I go to the vertice, then it's going to bisect that angle. So it bisects it here, and it bisects it here. All three of these angles may not be the same, but all three of them would be bisected, okay? And that's the one thing you should notice. Now, when I draw P down to the side, I'm going to draw it in perpendicular, okay? And if I go up here to this picture here, which is essentially the same picture, the three pieces that we're going to focus on here are those three right there, okay? The part that's different here is that it is perpendicular, right? Just like the last one was, but is D the midpoint of this side? We can just tell by looking, right? There's no way that D is the midpoint of this side. So it is not the perpendicular bisector, it's just perpendicular. So that's different, okay? It's not the same thing. Over here, difference between circumcenter versus incenter. Circumcenter, perpendicular bisector to the side. Here it's just perpendicular, not necessarily the bisector. But the three pieces that we're focused on here, once again, P is the incenter. The incenter will be the angle bisector of the triangle. So when I connect this, P is the incenter, and we're going to say that DP, EP, and FP are all equal to each other. So we really have to pay attention to the relationships and what kind of piece that we have. Okay, now using that, coming down here, essentially we have the same picture, we have different letters, we have different labels on it. What three pieces would be congruent in this picture? We've got three that we're looking for. Based on the picture at the top that we just labeled. The three that make what? Huh? And it goes from the end center to what? Does it go to the vertice or does it go to the side? It goes to the side, yeah. Because like here, does NA and NC look like it's going to be the same length? No. So if I go to the vertices, those don't look congruent, right? So the three that I'm looking at here are NF, ND, and NE. When I look at those three, NF equals ND equals NE. Okay. Now I could use any of these three, right? We know all three of these are equal, but I only really need two of them, and I'm going to use the two that we are given information about, ND and NE. So the first thing I'm going to do here is I'm going to say ND equals NE. And I know the expression for both of those. ND is really 5x minus 1. NE is really 2x plus 11. So we can set both of those equal to each other. And then once again, we're solving it for x. So I'm going to subtract 2x. I'm going to add 1. I get 3x equals 12. And I get x equals 4. Okay, now here's what we have to do. They're asking me to find NF. Well, I don't have an expression for NF to plug it back into. If I did, I would just plug it into that and I'd be done. But we know that NF is the same as ND and NE. So to find ND, I would do 5 times 4 minus 1, which is 19. To find NE, I would do 2 times 4 plus 11, which is 8 plus 11, which is 19. Once again, the fact that I get the same answer here is good news, right? If I don't get the same answer right here, I've done something wrong. And that's kind of a way you can check yourself. That's why it's good to do that like on a quiz or a test. Because if I'm getting the same answer, then that means I'm solving this out the right way, okay? Because those two should be the same. And if I know these two are both 19, what can I say about NF? It's also 19, right? All three of those are equal because that's what we said in the picture. Okay, now this question is a little bit different. They're asking us about NG. So if I were to draw this triangle right here, which is triangle NFG, right? It's this little blue one right here that I made. Okay. The one side that we know in this triangle is NF. We just found it up here. And so we're going to label NF with 19. The question is asking us, is it possible for NG to be 18? No, why not? It has to be bigger, right? We would say no. NG is the hypotenuse and must be the longest side. So what I would say here is that NG has to be at least greater than 19. Because 19 has to be smaller. 18 is not. So it's definitely not 18. All right, last one. Very similar to what we did. Once again, we're going to identify the three pieces that are congruent. PQ, MQ, and NQ are the three that we know are congruent, right? Because we know Q is the in-center. So over here, I'm going to say QM equals QN. They give me an expression for QM. 3x plus 8. I'm going to plug that in, substitute it in. QN is really 7x plus 2. Once again, it's just solving a two-step equation. Something we've done a lot of. So we get 6 equals 4x. So if I were to solve this for x, what would I get? 1.5? We can't get decimals. We can get decimals? Decimals are okay? Oh, okay. 3 over 2 would work, yeah? 3 over 2, 1.5. Don't freak out if you get decimals, guys, okay? It's going to happen. Decimals and fractions are a way of life, as much as we may not love decimals and fractions. If I measure a piece of wood someday in my life, or measure my yard or something like that I need to measure, not everything's going to be a nice equal 8 feet long, right? It might be 7.5 feet long. Then we've got to know it's going to be decimals. It's going to be fractions. Okay, so when I plug it back in, does that mean QM and QN have to be nice whole numbers? Not really, okay? They could be, but we're going to take this, we're going to plug it back in. And we're going to do 3 times 1.5 plus 8, which is 12.5. If I did QN, that would be 7 times 1.5 plus 2, which is also 12.5. So then QP has to be 12.5. Okay, that's all we got for today.